Math 230, Quest to College. I'm Joe Vasta. Today we're covering section 7.3, Probability with Counting Techniques. Before we get into it, we'll just do one puzzle today because this puzzle is kind of amazing here. And here is the puzzle. You and a friend will each choose one of these spinners. So you'll choose like one color, your friend will choose another color, and you'll spin it. The higher number wins. What is your strategy? What's the best spinner? So you think about that. Which one of these is the best spinner? Or maybe a better question would be, what strategy should you use? So that's the puzzle for this lecture. And now let's get into probability with counting techniques. A box contains 5 red marbles, 4 blue marbles, and 1 yellow marble, and we have it up right there. You randomly draw marbles out of the box. What is the probability you get a red and a yellow in that order without replacement? Okay, so there's a lot of words here, in that order without replacement. It does seem a little complicated. Well, let's think about this. It just seems like we have 10 marbles, and this would be our sample space, but our sample space is going to be a little bit more than this. Why? Because we're really drawing 2 marbles out of this box. So it's going to be a little bit more complicated, and suppose we pull out, we call this first marble red 1 and the second marble red 2, red 3, red 4, red 5, blue 1, blue 2, blue 3, blue 4, and then this one we'll just call it yellow. So one of the things that we can do is we can pull a red 1 followed by a red 2. Or we can pull out a red 2 followed by a red 1, or a red 1 followed by a blue 3, or a yellow followed by a red 4. So our box of marbles is going to be a lot bigger than this because there's a lot more outcomes that can happen. And here we have all the things that can happen. So here's red 1, red 2, red 1, red 3, red 1, red 4, red 1, red 5, etc. Red 1, blue 1, red 1, blue 2, red 1, blue 3, red 1, blue 4, and red 1, yellow. So that's all the ones where red 1 comes first. And then here's all the ones where red 2 comes first, etc. So this box, doing this experiment here, pulling out 2 marbles and looking at them and asking the question, even though it says we're pulling out 2 marbles, we reframe this question and you're really pulling out one of these marbles from this box. Now, how many marbles are in this box? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 times 10, so there's 90 marbles in this box. Let me write that down. There's 90 marbles. Okay, so our denominator is going to have 90 because there's 90 things that can happen. Now, how many things in this box that we want? We want a red and a yellow in that order, so it has to be in that order without replacement. So red and then a yellow. I see a red and a yellow here, and a red and a yellow here. In fact, I've highlighted them in this drawing right here. Those are the only 5 marbles in the box where we have red, then a yellow. So 1, 2, 3, 4, 5. And it does say in that order. So it has to be in that order without replacement. So 5 out of 90. Well, 5 out of 90, if you reduce it, you put 5 into 90 and 5 into itself, you get 1 out of 18. Okay, so that's great. But we do not want to do our problems like this. We don't want to draw out 90 marbles. So that's why this is called probability with counting techniques. We're going to figure out a clever way of doing these problems and getting 1 over 18 without drawing all this. So let's see if we can do this. A red and yellow in that order. Okay, in that order, we've seen that before. That means that order matters. And when order matters, that should bring up something. That maybe you're looking at permutations. So let's take a look at this problem again and do this problem without drawing all 90 possibilities. Okay, so we know our probability is a fraction. We know permutations we can do by using slots. On the bottom happens to be 2 slots because you're pulling 2 marbles out. Now, when you pull the first marble out, how many choices do you have? You have 10 choices. By the way, this is my fraction bar right here. Let me make the fraction bar be darker. So here's the fraction bar. So we're just pulling 2 marbles out. There's 10 choices for the first marble. Now look what it says. It says without replacement. So, like if I pull out blue 1, I'm not putting it back in. So then I would only have 9 choices for that slot, which gives me a 10 times 9, 90, which is how many marbles we have in the box. But we don't have to draw all 90 marbles. Now the top of this fraction is what I want, and I'm going to use slots to do that as well. Now sure, I could have used my notation 10 pick 2, but I didn't want to do that. I wanted to do it this way using slots. Now look at the top. What does it, the top is what I want. I want a red. I want this one to be red, and I want this one to be yellow. Okay, now how many choices do I have for reds? I have 5 choices. And how many choices do I have for yellow? I mean, even though I took the red out, it doesn't really matter. I only have 1 choice for yellow. Look what I have on the top. I have a 5. So this means we can do problems like this without drawing all 90 possibilities for the sample space. We used counting techniques. So what does this give me? It gives me 5 over 90, which is the same answer. Now I want to show you something really cool because I have a better way of doing this. We have 5 times 1 over 10 times 9. I'm going to write this a little differently. I'm going to write 5 over 10. Multiplied by, and then look, 1 over 9. That's the same thing, because when you multiply fractions together, you can multiply the tops and multiply the bottoms. So 5 times 1 is 5. 10 times 9 is 90. Now why did I do that? Because I'm going to show you a really cool way of doing this problem. When you get a problem like this, and it says in that order, it's a permutation, we're going to be very happy about this. So that's a happy face, because it says in that order, which means it's going to be a lot simpler than we think. So what you do is you say, okay, I want to pull out a red. So I might just go ahead and reproduce this down here. So I have red, 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 blue, 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 and then a yellow. So I can start by saying, well, what is the probability I pull a red out of this box? 5/10, and that's where I'm getting this fraction. Now watch this. Because it says without replacement, I cross out one of the reds, or I take it out of the box. Now my box only has how many marbles in it? It has 9 marbles, and then we say, what's the probability of pulling out a yellow? 1 yellow out of 9, 1/9. And so I can do the problem when it says in that order, 1 marble at a time, and when it's without replacement, I can cross out the marbles as I pull them out. One other thing that I want to show you with fractions is when I'm multiplying fractions together, yes, I can go 5/90, but it's a lot easier to reduce a top with a bottom before you multiply out. So 5/10 becomes 1/2. Then I can multiply 1 times 1 on the top and 2 times 9 on the bottom. 2 times 9 is 18. Now if you're sitting there going, what just happened? What is he doing? I'm going to go ahead and do a lot of similar problems, and by the time hopefully we're done with section 7.3, you'll have confidence when you do your homework. So let's go ahead and do another problem. If you're a little confused, I think a few problems will clear up that confusion. Okay, red. What is the probability of getting a red and a yellow in that order? So we know that these are permutations. I'm going to put a happy face near that. And this says with replacement. Okay. So the last one says without replacement. This one says with replacement. But when we see those words in that order, it means I can do it 1 fraction at a time. Okay. So I'm going to start off with the red. What is the probability of pulling a red out of that box? Well, it would be 5 reds over 10 marbles. Okay. Now I'm going to go ahead and multiply this, because these are permutations, by the next fraction, which would be the fraction of pulling a yellow out. Now remember on problem number 1, when I pulled a red out, I crossed it off. That's because that problem was without replacement. This one is with replacement. So I pull the red out, but guess what? I put the red back in, because it says with replacement. Okay, so now what's the probability you pull a yellow out of this box? The probability of pulling a yellow out of this box that has all 10 marbles is 1 out of 10. Okay, so this is for the red, this is for the yellow. Just like the last problem, except this one is with replacement. So the last problem looked like 5/10, and then it was 1/9. The 9 was because when you pull out that red, it stays out. So let's go ahead and multiply this out. I'm going to go ahead and be a little redundant in case someone's looking back at these PDFs and they are wondering what happened. I'm going to cancel that right there, the 5 and the 10, so that gives me 1/2. And my final answer on this is 1 over, multiply the denominators 2 times 10, which is 20. One thing that I do want to mention, when you have a 2 on the bottom and a 10 on the bottom, you cannot cancel things on the bottom with each other. You can only cancel something from the top with something from the bottom. Okay, so I've seen people cross out the 2 and the 10 and write a 1 and a 5, and that's bad. You don't want to do that because those are both in the denominator. So this takes care of problem number 2. Let's go ahead, and I don't know how this is going to work because I thought the marbles were too big last time I did this, but I'm going to go ahead and use these plastic pieces. I think they are too big. Oh well, what are you going to do? So there's that. There's 4 of these. In fact, what I'm going to do, I'm just going to cover up that box there because this says the same thing here. And then, what else do we have? We have a yellow marble. Okay, here's the yellow marble. What is the probability of pulling out 2 reds and 2 blues in that order without replacement? Okay, so this says in that order, we're going to put a happy face there. Why? Because we can do it 1 fraction at a time. Here's the box. In fact, let me draw the box with a Sharpie pen. If I do that, it usually trails beneath. Great. Okay, we have that and that. Okay, let's go ahead and do these problems then. And you'll see that they're not that bad. I don't know why I keep touching the marbles. I'm trying to adjust them and they still look kind of crooked. Okay, we can do this 1 fraction at a time. This is without replacement. So let's pull out the first red. The probability of pulling out that first red is 5 out of 10. So let's pull out that first red, and we keep it out because it says without replacement. Now what's the probability you pull out another red? Because this is in that order, so we're going to multiply this by 4 out of 9. So we pull out that red. Basically, I'll go ahead and put the reds down here, so I pulled those out there. Okay, so now we want to pull out a blue. What's the probability of that happening? Well, the probability of that happening is 4 out of 8. 4 blues out of 8 marbles. So we pull out one of those blues. And now, the last blue. What's the probability of pulling out the last blue? Well, there are 3 blues left out of how many marbles in the box? 7. So I'll pull out that last blue. And so this is what I want. I want red, red, blue, blue when I do this experiment. And you can see on the bottom we have 10, 9, 8, 7. That is 10 pick 4 on the bottom. These are permutations. We can multiply these fractions together because it says in that order and these are permutations. So let's go ahead and do that. I'm going to write this out. I'm being redundant. And what we're going to do is we're going to experience a canceling party where we cancel things. So the 5 over 10 becomes 1/2. And then I have a 4 and an 8, so those can cancel. This becomes 1/2 as well. And the 9 and the 3, that becomes 1/3. Does anything else cancel with that 4 up there? Why, it does. Look, this 4 and those 2s all will cancel out. And when they go away, there's still something there. There's still 1s there. So on the top I have 1 times 1 times 1 times 1, which gives me 1. And on the bottom I have, if you read through this mess, 1 times 3 times 1 times 7. So that's really 3 times 7, which is 21. 1 over 21 is the answer to this probability question. Okay. So let's go ahead and put the marbles back in the box. It doesn't really matter. They're really supposed to be all mixed up, but we do it this way because it's easier on the eyes. And let's see if we can do some more problems here. What is the probability of getting 2 reds and 2 blues? It looks like the problem up there. In that order, which I'll put a little happy face by. You're like, is there going to be ones where you put a sad face by? Well, just keep watching the video. In that order with replacement. Okay. So in that order means I can do it 1 fraction at a time, 1 probability at a time. I want to pull out a red. What's the probability of that happening? 5 reds over 10 marbles. So 5/10. I pull the red out. Guess what? It says with replacement, I put the red back in. Okay, my next one has to be a red. So what's the probability of getting a red? Well, 5/10. Pull the red out. It says with replacement, put the red back in. Now I need a blue. What's the probability of getting a blue? Well, 4 out of 10. Pull the blue out. Put the blue back in because it says with replacement, and the probability of pulling out a blue, 4/10. So these are my 4 fractions. I'm going to multiply them together. I'll go ahead and rewrite them. I'm not saying that you should rewrite your fractions before you start having your counseling party, but I'm doing that because I do realize people are looking back at the PDFs, and it might be too confusing if you want to see this, but you see lines, you see it's all scratched out there. It's a little harder to see. So my counseling party, we have 5/10 is 1/2. 5/10 is 1/2. 4/10 is 2/5. And 4/10 is 2/5. Now the party's not over because we have 2 2s on the bottom and 2 2s on the top. And so you'll cancel, you'll get 1s there and 1s there. So on the top I have 1 times 1 times 1 times 1, which is 1. On the bottom I have 1 times 1 times 5 times 5, so 5 times 5 is 25. And so yeah, it does make a difference whether you have without replacement or with replacement. You see those probabilities are different. A few things to mention before we move on. In a statistics class, when you go in that order with replacement, sometimes they call that independent events. And with independent events, you can multiply the probabilities together. I'm taking a different approach. You're not going to see this approach in a standard statistics class. I just find this approach easier to understand. Another thing to realize is the sample space for this one right here. If you drew out all the possibilities that can happen, it would be 10 times 9 times 8 times 7. That would be a lot of marbles. It would be thousands of marbles. Whereas this one would be 10 times 10 times 10 times 10 if you drew out all the possibilities, and that would be, I think, 10,000. So yeah, that is, let's see, 4 zeros. 1, 2, 3, 4. Yes, that would be 10,000 marbles you'd have to put in a box and say, oh, one marble would be red 1, blue 2, red 1, yellow, and then another one, and it would just take forever to write out all the sample space for this. So that's why we are using these counting techniques. Why don't we move on to the next problem? The next problem is similar. Messing up my marbles here. And so what does the piece of paper, it just looks like that. I didn't plan this out very well, did I? I mean, I put that up there to remind you what you're doing. But all the action is happening right here. Okay, so let's go ahead and put this right there. put those marbles back in the box here. Okay, you might pause the video and see if you can do these ones on your own. What you see on both of these is you see in that order, that's a happy face. In that order is a happy face. Okay, so that's a really big mouth for that face, but we're really happy that we can just multiply the probabilities together. Let's go ahead and look at the probability of getting a blue and 3 non-blues. In that order, without replacement. Okay, so let's start off our first fraction. We want to get a blue. What's the probability of getting a blue? Well, 4 out of 10. Okay, we're going to multiply that after. Okay, so let's pull out our blue. So we pull out a blue. I'll just put it right there. And the next thing I want is a non-blue. So a non-blue would be anything that is not blue, red or yellow. So what's the probability of pulling out a red or a yellow? It would be 1, 2, 3, 4, 5, 6. 6 out of 9 marbles. So let's pull out this non-blue right here. And now we need to pull out another non-blue, okay, because we have to pull out 3 of them. So the probability of pulling out a non-blue, there are 1, 2, 3, 4, 5 non-blues. 5 out of 8 marbles in the box. Okay, we'll pull out another non-blue. And now we have to pull out our last non-blue. What's the probability of that happening? Well, how many non-blues do I have? 1, 2, 3, 4. 4 out of how many marbles in the box there? 1, 2, 3, 4, 5, 6, 7. 7. And so we pull out our last non-blue. And that's what we want. We want a blue followed by 3 non-blues. And so here are the probabilities that I have to multiply together. So I'm going to go ahead and put things back in the box, and the rest will just be multiplying some fractions out. So I'm going to go ahead and be redundant. 4/10 times 6/9 times 5/8 times 4/7. And on the bottom you can see the 10, 9, 8, 7. So you do see the permutation. Let's go ahead and cancel. We're at our canceling party. I see a 5. I see a 10. Let's cancel those. So this is going to give me 1/2. I see a 4 and an 8. That's going to be another 1/2. 6 and the 9, well, I think that can reduce to 2/3. What else do we have? We have, there's many ways of doing this party here. We have a 4 up there, and then we also have 4 down there. So those cancel out. Those are all 1s now. And after that mess is over, we have 1 times 2 times 1 times 1 on the top, which is 2, because of that 2 there. And on the bottom we have 1 times 3 times 1 times 7. So 3 times 7 is 21. I think it's 21, yeah. And so our final answer is 2/21. And this is a really complicated problem, but we were able to break it down into permutations and multiply fractions together, multiply the probabilities together. And for some of you, the hardest part of this problem might be just simplifying this. Because we really don't want to multiply out 10, 9, 8, 7 on the bottom, and then 4, 6, 5, 4 on the top, because then you'll have a major reducing job to do, and it's harder to reduce that way. Let's go ahead and do problem number 6. What is the probability you pull out a blue and 3 non-blues, in that order, happy face, with replacement? So the probability of pulling out a blue is 4 blues out of 10 marbles in the box. Pull the blue out, and guess what? Put the blue back in because it says with replacement. What's the probability you pull out a non-blue? Well, there are 1, 2, 3, 4, 5, 6 non-blues out of 10. Pull out a non-blue, put it back in, do it again. 6 out of 10. Pull out the non-blue, put it back in, and then 6 out of 10. So with replacement, some of you might think with replacement looks a little easier because you don't have to keep track of how many things are in the box, and it just looks a little simpler. So let's go ahead and be redundant here. 6/10, 6/10, 6/10, and then we'll reduce. So we have 4/10 is 2/5. 6/10 is 3/5. So we do that 3 times. Nothing else can cancel because you have all 5s on the bottom, and then you have a 2, a 3, a 3, and a 3 on the top. So on the top, I'm going to go 2 times 3, that's 6. And then this 3 times 3 is 9. So 6 times 9 is 54. And on the bottom, I have 5 times 5 is 25. Times 5 is 125. 125 times 5. 25. 10, 11, 12, carry the 1, 5, 625. So we have 625 on the bottom. We know that's reduced because nothing else can cancel over here at our counseling party. That would be sad if you were having a counseling party and the police came and they said you can't have that anymore. So you guys were too loud or whatever. I don't know what happens at counseling parties. Let's go ahead and do some other kinds of problems. Now notice, the 6 problems that we did said in that order. In that order. Okay. So what happens if it's not necessarily in that order? And that's what we're going to do now. Okay, a red and a yellow. Not necessarily in that order, without replacement. Okay, wow, so how are we going to do this? This one's going to be a little bit more complicated to do. Okay, the not necessarily in that order, so we'll take a look at that. Well, that really means that order doesn't matter. And when order doesn't matter, what does that mean? That means we're looking at a combination. We're looking at combinations. I'll just put combination. So we're considering combinations now. Combinations without replacement. So this without replacement says without reps. And those are the ones that we learned in the last chapter. So let's go ahead and set up a big fraction. We can't use slots, but let's look at it this way. The bottom is anything that can happen when you pull 2 marbles out. Combinations without reps. So when you pull 2 marbles out, you have 10 marbles to begin with, and you're choosing 2 marbles. So this is 10 choose 2 on the bottom of the fraction. Okay, so now the other problem, when we did permutations, we had the slots, but we could have said 10 pick 2. So this one's 10 choose 2. Now the top is what I want. So I want 1 red and 1 yellow. So my first task is choosing 1 red. How many reds do I have to choose from? 5. So I'm going to write, even though it might be a little more complicated for this problem, I'm going to write 5 choose 1. So that's my first task. I'm going to multiply that by, so that takes care of the red. Now I'm going to choose the yellow. And that is, how many ways can I choose 1 yellow from 1 yellow? That's 1 choose 1. Now a lot of you would have just preferred on the top to just go, there's 5 reds, 5 times 1. Okay, but it will get a little more complicated in the next two examples, so this is why I'm setting it up this way. Now, here's the deal when you have combinations. 5 choose 1 is 5. 1 choose 1, go to row 1, 1. 10 choose 2, 45. So this is 5 times 1 all over 45. That came from Pascal's triangle. So now what I'm going to do is I think I can reduce this 5 and this 45 to 1 over 9. And then there's a 1 times 1 on the top and a 9 on the bottom. So this is 1/9 for my answer. Okay, so when it's not necessarily in that order, it's not as simple. You can't just go fraction by fraction. You have to use combinations. And we'll do a few more problems like this to make you more comfortable with this. So not necessarily in that order. The face that I'm going to use is not a sad face, because the sad face would mean that we couldn't do it, but maybe a neutral face. So let's go ahead and see if we can do ones that are more complicated than number 7. Not necessarily in that order is kind of what we're looking at now. So let's see if I can take this off. We have this right here. Problem number 8. What is the probability of getting 2 reds and 2 blues, not necessarily in that order, without replacement? Okay, so not necessarily in that order, I'm going to go ahead and put the neutral face. Okay. I'm going to have to use combinations. Okay, so this is how we're going to do it. We're going to set up our fraction. We won't use the Sharpie this time. And the bottom is all the things that can happen. We're pulling out how many marbles from this box? We are pulling out 2 and 2. So we're pulling out 4 marbles from the box. Well, using choose talk, how many ways can I choose 4 marbles from this box? And the number of ways of doing that would be 10 marbles, choose 4. Now the top of my probability is what I want. I want 2 reds and 2 blues. Let's go ahead and choose the reds first. How many ways can I choose 2 reds from 5 reds? Well, that would be 5, choose 2. That's a comma there. And then we're going to multiply this by, now let's go ahead and choose the blues. How many ways can I choose 2 blues from 4 blues? That would be 4, choose 2. Now this might remind you, the top of the fraction might remind you of like when you had different groups of people, like girls and, let's say, boys and girls and a cat. And how many ways can you choose, you know, 2 girls and 2 boys to be on your committee? It would be 5 choose 2 and then 4 choose 2, and you'd multiply them together. So this was the last kind of skill we learned when we did the chapter on counting. So what am I going to do now with this? I'm going to go to Pascal's triangle and look up those combinations. 5 choose 2. That would be 10. 4 choose 2. That would be 6. And 10 choose 4. 2, 3, 4. That would be 210. So this was Pascal. I'll just say Pascal here. Let's go ahead and have the reducing party. Well, look at this. The 10 and the 210. 10 goes into 10 1 time, and 10 goes into 210 21 times. And at any time, if things look a little complicated, you can always rewrite it, like 6 over 21. And then does anything go into 6 and 21? Yes, 3 does. 3 goes into 6 2 times, and 3 goes into 21 7 times. So my final answer for this is 2 over 7. And there it is. So you might think about pausing the video and seeing if you can do this one on your own. Okay, my first step says not necessarily in that order is a neutral face because I have to do combinations. Okay, I'll just abbreviate it. And we have a fraction. I didn't give myself a lot of space for these, did I? But I wanted to fit the marbles for some reason. Okay, so how many marbles am I pulling out of the box? I'm pulling a blue and 3 non-blue. That's what I want, but I'm pulling out 4 marbles for this experiment. So it's going to be like the last problem where I'm going to go 10, choose 4. Now the top is what I want. So let's take care of the blues first. I want 1 blue from 4 blues. So that's going to be 4, choose 1, multiplied by, now let's take care of the non-blues. I have 6 non-blues and I'm going to choose 3 of them. 6, choose 3. I'm going to go to Pascal's triangle and look up some of these things. Well, I know that 10 choose 4, we did that in the last problem, that's 210. And I know 4 choose 1 is 4. So let's use Pascal's triangle to do 6 choose 3. 1, 2, 3, that's 20. Okay, now we'll reduce this. Let's see, 20. 10 goes into 20 2 times. 10 goes into 210 21 times. So I have a 21 on the bottom, which is really 3 times 7, and then I have a 4 and a 2 on the top. So I don't think I could reduce this anymore. 4 times 2 is 8, and on the bottom you have 21. And you can look at that and see that it is reduced. That is the answer to this problem. So for some of you, these are going to probably be the worst problems in Chapter 7. They shouldn't be. I mean, if you practice a few, you should go, oh yeah, I know how to do these problems. They're really not that bad. But the thing is, we're taking stuff from the last chapter, our counting skills, and we're using them here. Now, we're never going to get in this class not necessarily in that order with replacement because we never really covered combinations with replacement. I may have showed it to you like as an extra optional topic, but we're not going to do that. So anytime you see not necessarily in that order, you'll also see without replacement in this class. Okay, things can always get more complicated, and you know, we really don't want to make things that really complicated. Okay, our next problem, problem number 10. So let's get rid of this. And this one right here. So for some reason I left a lot of space at the top because I knew I was going to be doing this. This says, what is the probability of getting 2 blues without replacement? Okay, so what's not written here is in that order, and the other one that's not written is not necessarily in that order. Okay. Let's go ahead and do not necessarily in that order. Not necessarily in that order. I could have just written N-N-I-T-O, nanito. Maybe I'll do that next time. But not necessarily in that order. Let's do that one first. So I didn't actually specify if order matters or not. So let's just do the combination one since we already did that. Okay, how many marbles am I pulling out of the box here? I'm pulling out 2 marbles. So the bottom of the fraction says we take care of 10 marbles, and we're choosing 2 of them, so 10 choose 2. Now the top of the fraction is what I want. I want 2 blues, and I'm going to choose them from 4 blues. So it's going to be 4 choose 2. I'm going to look these up on Pascal's triangle. 4 choose 2. 6. 10 choose 2. 45. I'll reduce the fraction. I believe 3 goes into each of those. 3 goes into 6 2 times. 3 goes into 45. Do a little no shame over here. 15 times. So my final answer is 2 over 15. Okay, now let's go ahead and do problem number 10. In that order. Now, in that order's one where I can just do one probability at a time. So what is the probability I pull a blue out of this box here? Well, the probability would be 4 out of 10. Whoa, I've lost the blue. It's gone. It's down on the ground. Okay, it's without replacement, so I really didn't have to get it. Because now I'm going to pull out another blue, and the probability of that happening would be 3 out of 9. Okay, so here's the first blue that I retrieved, and then here's the second blue. That's what I want. Okay, so let's multiply those fractions together. Before I multiply, let's see if we can reduce. The 3 over 9 becomes 1/3. The 4 over 10 becomes 2/5. So it looks like my final answer is 2/15. Okay, we'll put those blues back in. And what do you notice? Those are the same. Now, were they the same in the older examples? I'm going to probably be a little confusing for some people. See that it was 2/15, 2/15. So really that didn't matter if I said in that order or not necessarily in that order. If you look at problem number 7 and problem number 1, this was without replacement with that. On one of them it was a 1/9. So problem number 1 was 1/18 and problem number 7 was 1/9, and that was pulling a red and a yellow out without replacement. Not necessarily in that order, and in that order gave me different answers. What makes this problem so different? And you can check out some of the other ones like 8 and 9. Those gave me different answers than the ones that I did in that order. Well, what makes problem number 10 so different than the other ones is the fact that I'm just pulling out one color. So in 1 through 9, all those problems I was pulling out different colors. And this is the first problem where I was pulling out the same color. So what is the lesson to be learned? The lesson to be learned is when you are doing a problem where you're just pulling out the same colors, then it doesn't matter if you take the not necessarily in that order approach or the in that order approach. And so because the in that order approach is simpler, I will always take that approach when I'm pulling out the same color. So we'll do some more examples on this. Number 11. So what's the probability you pull out 2 blues with replacement? Okay, I'm going to do the in that order approach. In fact, the not necessarily in that order with replacement, I already told you that we're not covering that in this class, but both would yield the same answer. So let's see what I get when I do this. What's the probability I pull a blue out of that box? 4 out of 10. Take the blue out with replacement. Put the blue back in. What's the probability I pull a blue out of that box for the second blue? It would be 4/10. So let's go ahead and write this down again to be redundant. 4/10 times 4/10. So we can reduce each of these. 2/5. 2/5. Nothing else cancels, so I end up getting for my final answer 4 out of 25. So I'm going to go ahead and put this one up. After problem 13, we're going to switch it over to miscellaneous problems, and we'll stop doing this. Okay, so this has been the same box for the first 13 problems. What I would like you to do, if you've been paying attention to this, is I would like you to see if you can get the correct probabilities for 12 and 13. Try to do those problems on your own. And notice with these problems, it's all the same color, so you can pick whether you want in that order, which that's the one I would pick, or not necessarily in that order. Okay, so let's do the problems. The probability of getting 3 reds without replacement. Okay, I'm going to go with in that order because it's just 3 reds. So what am I going to get? Probability of pulling a red out is 5 out of 10. Now some of you might be watching this lecture going, wait a minute, Joe, why don't you just put a 1/2 there? 2 reasons. It's funnier this way, okay, to torture people. But the second reason is when people are looking back at the PDFs, they can actually see where these numbers came from. There were 5 reds in the box out of 10. So this is, I want to actually write 1/2 when I do some of these problems. But for the sake of teaching, I'd like to just put this, and then I'll reduce that. Okay, without replacement, what's the probability you pull out the next red? 4 out of 9. And the third red, that would be 3 out of, there's 8 of them. So what you have is you have 5 pick 3 over 10 pick 3. We don't really have to say that, but that's what it is. And so we're going to multiply those fractions together. I'm going to put these back in the box, and I'll do this redundant thing that I've been doing here. Okay, can anything cancel? Yeah, the 5 over 10 becomes 1/2. The 4 over 8 becomes 1/2. And the 3 over 9 becomes 1/3. So I have 1 times 1 times 1 on the top, which gives me a 1. And then I have 2 times 3, which is 6 times 2, that's 12. 1/12 is the answer. Now what is the probability I get 3 reds with replacement? Okay, what's the probability you pull a red out of that box? 5/10. And I can do this in that order. I can do it 1 fraction at a time because it's all the same color. Pull the red out. Put the red back in. What's the probability of pulling out a red? 5/10. Pull the red out. Put the red back in. Why? Because it says with replacement. Probability of pulling out that third red would be 5/10. So 5/10 really is 1/2. This is 1/2 times 1/2 times 1/2. 1 times 1 times 1? 1. 2 times 2 times 2? That's 8. So 1/8 is the answer for problem number 13. And you can see, with replacement, without replacement, it does make a difference. Let's go ahead and do some miscellaneous problems. We'll get rid of, so this says miscellaneous. Okay. Rid of this here. Yeah, maybe I'll just get rid of all of this. A candy dish contains 9 jelly beans. 4 of them are poisoned. Okay, so that's bad, isn't it? So the poisoned ones will make red. Which means how many good jelly beans are there? There are 5 good jelly beans. Now they're all mixed up, but I kind of just put them like this. Okay, so there it is. There's the box. If 3 jelly beans are randomly selected from the dish, find the probability that all 3 jelly beans are not poisoned. Okay. That's good to know. So you can see your probability of living. So it's just like the marble problems, but we have to determine the question about order, and we also have to determine replacement. So really what we want is, what is the probability all 3 jelly beans are not poisoned? So that just means we want 3 good ones or 3 green ones. Okay. Now is this with or without replacement? Because order, not necessarily in that order, and order, in that order, it really doesn't matter because I'm pulling out the same color. That's what I'm looking for. So really we just have to do with replacement, without replacement. Well, when someone says, hey, go to that dish of jelly beans and select 3 of them, usually what they mean is you go in there and you pick 1, 2, 3. Okay, which means without replacement. Okay. So I'll make my without like that. Without replacement. So let's see if we can do this problem. Because it's all the same color, I'm going to do this using permutations in that order, which means 1 fraction at a time. What's the probability I pull out a green jelly bean? Or a green marble? Would be 5 out of 9. Pull it out and keep it out. So we'll put it down here. What's the probability I pull out another green given this situation? That is 4 out of 8. Okay, what's the probability I pull out a third green jelly bean? Well, it would be 3 out of 7. So that's what I want. And if I pull out a poison one and then eat it, then I'm going to die. So this is really my probability of living if I want to grab 3 jelly beans from that dish and eat them. Okay, let's put those back in the dish. We'll have our canceling party after I write this down again. And so the 4 and the 8 cancel, that becomes 1/2. The 3 and the 9 cancel, that becomes 1/3. And nothing cancels with the 5. So it looks like I have 5 times 1 times 1 on the top, which is 5. And on the bottom I have 3 times 2 times 7, so that's 6 times 7, that's 42. So your probability of getting 3 jelly beans that are not poisoned happens to be 5 over 42. Now I'm going to go ahead and write out what percentage that is. So the percentage that you survive this, maybe you don't know that 4 of them are poisoned. It would be a 12% chance of living, which seems pretty slim there. Shouldn't eat those jelly beans. Let's go ahead and do another miscellaneous problem here. And what I'll do here, what will I do? Green and red. I'll go ahead, for the sake of the PDF, and draw the 5 good jelly beans. And the 4 bad jelly beans. That's basically that last problem. So let's move those out of the way and do our next problem. A class contains 4 girls, which, since girls start with G and so does green, I'll go ahead and put 4 girls. and 5 boys. Boys start with B, and so does blue, so 5 boys. So that's what I have. A class contains that. If 5 people are selected at random from the class, what is the probability that 2 are girls and 3 are boys? So what's the probability that 2 are girls and 3 are boys? The question is, does order matter? Did they say the first one had to be a girl? No, they just said that 2 are girls and 3 are boys. So this is not necessarily in that order. And are we having replacement or not? Well, they didn't say replace them as you pick them. You're actually just selecting 5 people from a group of 9 people. So this is without replacement. Okay, so this is the one where we say, because we can't do it one fraction at a time, and we'll write our big fraction bar, and on the bottom, I always like to approach the bottom first. It's just the personal thing. How many marbles am I pulling from this box? I'm pulling 5 total. So it's going to be something choose 5. It's going to be 9 choose 5. So that's all the things that can happen. Now the top is what I want. I want to choose 2 girls or 2 greens from this box. So it's going to be 4 choose 2. Multiplied by now the task of choosing the boys. I want to choose 3 boys from 5 boys. That's going to be 5 choose 3. Okay, 4 choose 2 on Pascal's triangle. That's a 6. 5 choose 3 on Pascal's triangle. That's a 10. And 9 choose 5 on Pascal's triangle. That's a 126. So does anything cancel? I think the 6 goes into 126. 6 goes into 12 2 times. 6 goes into itself 1 time. So that's 21. So 6 goes into this 21 times, and 6 goes into itself 1 time. So our final answer for this happens to be 10 over 21. Oh, and this was one of those problems where we couldn't multiply out the fractions. The hard part about these miscellaneous problems is determining, if it's going to be not necessarily in that order or if it's in that order, and then the replacement. We have to decide that. Okay, let's continue. Do some more problems. We have probably like 6 more problems to do, and then we'll come back to that extra credit problem. What strategies should you use when you play the spinner game? And that's going to shock a lot of you. Okay, experiment. You spin the spinner 3 times. Here's the spinner. So we're going to spin that 3 times. Now when I spin the spinner 3 times, it's the same as having a box that has marbles 1 through 5, drawing from that box 3 times. And is it with or without replacement when you spin a spinner? Well, you can have repetition. You can have, this is with replacement. So what is the probability that you spin 3 2s? It's the probability you get 2, 2, 2. Of course, this is with replacement. It's the same color or the same number, so we can just do it one fraction at a time. The probability of spinning 3 twos, well, the first time you spin or pull out of this box, it's going to be 1 out of 5. The next time would be 1 out of 5, and this is with replacement. And then the last time is 1 out of 5. And once again, in a statistics class, they would call these events independent events. And then they would say you can multiply the probabilities together, and they may not mention it's because these are permutations. So 1/5 times 1/5 times 1/5, well, 5 times 5 times 5 is what you're really doing, and that's going to be 125. We're doing these last 6 problems to help us work towards something called the birthday paradox, which we'll cover in the next section, which is really fascinating. What is the probability that you spin no 2s? Okay, so probability that you spin no 2s, so I'll stop writing that on some of these problems. Well, what's the probability you spin this and you get something that is not a 2? Well, there are 4 non-2s in there, so it's going to be 4/5. It's with replacement, and it's all the same thing. No 2s, no 2s, no 2s. So I mean, we can do that in that order. Times 4/5 times 4/5. Okay, nothing cancels with those 5, so we know we have a 125 on the bottom. 4 times 4 is 16. 16 times 4 is 64. So we have a 64 on the top. Next problem. What is the probability the first number is odd, the second number is at least 2, and the third number is even? Okay, so this is in that order, and there's 3 different things that are happening. So the probability the first number is odd, the second number is at least 2, and the third number is even. Okay, so this is in that order. The reason we didn't have to actually write in that order on these 2 is because these were all the same type, all the same color as we did in the other example. 2, 2, 2, non-2, non-2, non-2. So that we did it in that order because we could choose to do it that way. And then this is with replacement. It's all with replacement with the spinner. Okay, what's the probability you spin an odd number? Well, there's 3 odd numbers out of 5 multiplied by. The second thing is at least 2. At least 2 means 2 or more. So 2, 3, 4, 5. That's 4 things that we would like on that out of 5. Even. How many even numbers do I see in here? 1, 2. 2 out of 5. Once again, nothing's going to cancel with those 5s. And so we end up going 3 times 4 times 2. So 3 times 4 is 12. 12 times 2 is 24. 24 out of 125. And we know it's reduced because there was no canceling that we could do over here. Okay, so let's take a look at the last 3 problems of this lecture. What is the probability that all 3 spins give the same number? So this one's going to be a little freaky. Okay. All 3 spins give the same number. Now I could draw the box and put the marbles in there and say 3 times with replacement. But the deal is, this one's really weird. I mean, it could be a 444 or 111. Let's do the probability. Maybe I will put the box. I like the box. 1, 2, 3, 4, 5. 3 times. This is with replacement. Okay, now, when you spin the spinner the first time or reach into that box to grab one of those marbles the first time, the first time it could be any one of the marbles, because you're not going to be breaking this rule. I mean, you want all 3 spins to give the same number, so the first probability is 5 over 5, because it's not, you can select any number for this experiment. But suppose the first number that we selected was like a 4. Okay, so suppose that was the first number. Then the next time we drew from this box or spins the spinner, the next time you would need to get a 4, wouldn't you? Because you have to have all 3 spins give the same number. So your next probability would be 1/5. And so suppose you got a 4 there. Well, the last one would also have to be a 4, which would be a 1/5. So that's weird in this problem, how we would start off by saying 5 over 5, but that's because it says the same number and they didn't specify the number. Now, if they said all 3 spins give a 5, then you'd have 1/5, 1/5, 1/5. But because they say the same number, they didn't specify that number, the first probability says you can get anything. So, if we see this as a 1, 5 over 5 is 1, then you really just have 2 5s on the bottom, and this is 1 over 25. Okay, you might want to try to do some of these on your own. If not, let's go ahead and do this. What is the probability you spin 3 different numbers? Okay, well, when you spin 3 different numbers, let's think about this. The very first time you spin the spinner, it can be anything, just like in problem number 19. So the first probability is going to be 5 over 5. And let's say that first number that you spin is a 2. Well, you're trying to get what? 3 different numbers. So the second time it cannot be a 2, so the probability of not getting a 2 would then be 4 out of 5. And so let's just put another number up here, like maybe, let's say the second time you spin the spinner, you get a 5. You want 3 different numbers, so that third time it cannot be a 2 or a 5. So we'd have to cross those out. We'd only have 3 out of 5 choices. So the probability that you spin 3 different numbers would be this guy right here, with the 5 over 5 being 1, so I really just have 4 times 3 on the top and 5 times 5 on the bottom. Okay, what is the probability you spin 3 different odd numbers? Okay, so once again we see those things say different there. Okay, the first time you pull from this box, it has to be an odd number. How many odd numbers do you have? 1, 2, 3. You have 3 odd numbers out of 5. So let's say the first odd number that you spin is a 5. I should finish this and say maybe a 1 there, I don't know. Okay, so if you spin a 5 the first time and you're trying to get different odd numbers, then you only have 2 more odd numbers that you can spin, a 1 or a 3. So the probability of that would be 2 out of 5. So let's suppose you spin the 1. Then that last one you absolutely have to spin is a 3, because there's only 3 odd numbers up there, so that probability would be 1/5. And so, you would have to spin a 3 to get this. So this gives us 3 times 2 times 1, which is 6 on the top, and 5 times 5 times 5, that is the 125 on the bottom. And that completes this section, but we really want to see the deal with the spinners. Okay, so this is rather famous. And why is it famous? It's famous because it's kind of neat. You'll see. So you want to actually figure out the strategy for this. Which spinner is better? Well, why don't we just go ahead and do this? Let's go ahead and put blue and green on a table. So remember, green is kind of a dumb spinner because anytime you spin it, you know exactly what's going to happen. It's going to be a 3. But the blue, it could be a 4 and it could be a 0. So the green spinner is at the top. It's all 3s. And the blue spinner I'll put on the column, and it's 0, 0, 4, 4, 4. So when I compare this, if blue spins a 0 and green spins a 3, then green wins, and I put a G there. Okay. Now if blue spins a 4 and green spins a 3, so we go right here, so we look at this. Let's use the right colors here. Green spins a 3 and blue spins a 4, then who wins? Blue wins, and that's why I put a B there. So what it looks like when you fill in this table, and there are actually 36 things that we can fill in, it's like rolling 2 dice, really. Blue wins 2/3 of the time. So I'm going to say blue is greater than green. Okay, so if you just had these 2 spinners, and the red and the orange one weren't there, you would say, okay, I want the blue one, and then your friend has to pick the green one, and then you're going to win 2/3 of the time. Now let's see how green and red compare. Green's the one where you're always spinning a 3, so I'll put that along the column, and the red's the one where it could be 2, 2, 2, 2, 6, 6. And so red versus green. So there's green, there's red. So like if red spins a 2 and green spins a 3, green wins. So anytime red's number is less than green, we put a G. But like if red spins a 6 and green spins a 3, we end up having red win. But look at this. Green wins, and you can look at this up here. You can compute the probability. I mean, you can say that there's 36, and then there's 1, 2, 3, 4. There's 24 out of 36. So green wins 2/3 of the time. So green is greater than red. So that's interesting. So blue is greater than green. Green is greater than red. Let's compare red with orange. And I know that kind of looks a little yellowish. Here's red. Okay, so orange has 1, 1, 1, 5, 5, 5. So orange, 1, 1, 1, 5, 5, 5. And then red has 2, 2, 2, 2, 6, 6. And if you do the same thing, you see that you get a lot more reds winning than oranges. So red wins 2/3 of the time. Red is greater than orange. Okay, so this is how it goes. Blue is greater than green is greater than red is greater than orange. So the deal is, if you stop right there, you might say, okay, I want the blue one, and I don't care what the other person gets because we figured out that blue was the greatest. Now I'm going to compare blue with orange. Look what happens. Here's orange, 1, 1, 1, 5, 5, 5, and here's blue, 0, 0, 4, 4, 4, 4. So we have this, and when blue plays against orange, orange actually is better. Orange wins 2/3 of the time. So orange is greater than blue. Wow, so look what we have. We have blue is greater than green, is greater than red, is greater than orange, which is greater than blue. That's what we have right there. So these are non-transitive spinners because we thought there was a pecking order, but there's not. And this actually upsets a lot of us because we think, you know, when we're using the greater than sign that it has to be transitive. That means we can't put blue over here, but that's exactly what happens on this. So what the strategy is, and this is kind of a funny strategy. So the strategy is be polite. What does that mean? The strategy is let your friend pick the spinner. Because if your friend picks the spinner, like let's say your friend picks this spinner, then you pick the blue spinner and you beat your friend. So blue beats green. If your friend picks red, you pick green and you'll beat red. If your friend picks orange, you pick red. Red beats orange. Okay, so we'll just say beats. But then you might be thinking, well, what if your friend picks the blue? Well, then you pick the orange. Orange beats blue. So if you're polite, then you let your friend select the spinner, and you always pick the one that's right above it, or you know, if it's the one that at the top, you pick the orange, and you'll always have a 2/3 chance of winning. Now this thing that we did was actually called the Ephron Dice. So this Ephron Dice here has, someone actually bought me these. I think a student of several years ago. This has 4 4s and 2 0s. The zeros don't have any spots on them. And then this one right here, I think, was the orange one. This was 3 6s. No, 2 6s and 2 6s and 4 2s. And then this one was this is a good die here. It just has 3s on it. And so it would be a little nice if these dice were different colors, but maybe not. You know, maybe you can just kind of remember that. And so they actually do sell. You can go online and see the Ephron. That was a person's name. Dice. And I made it spinners because it's easier to explain with the spinners. You can see everything on the spinners. And so that is the deal. Probability has this weird thing going with it, where we've already seen at the end of section 7.1 that people can use probability for evil, and we had that one situation with the poison candy and all that stuff, but you also have this thing where we have non-transitive dice, but we can use probability to show us that they really are non-transitive. Well, this completes section 7.3. Make sure you keep up with the homework. Have a good day, and I'll see you in the next video.